would you like to start recording?
Recording
Yes.
in progress.
Thank you. Well, good evening, everyone. Good afternoon and morning, wherever you are. We're from nexMPI, which is Cost Action Finance Network. We are starting a webinar series featuring alternating themes designed to engage both the general public and scientific community. The series will include accessible introduction to magnetic particle imaging, as well as an in-depth expert sessions. For today, we have Patrick Vogel from Germany, from Julius Maximilians University in Würzburg, and also Phase Vision in Germany as well. Patrick is recognized for his contribution to experimental physics and MPI with deepest interest in, and as a founder as Phase Vision as well. I would say Patrick's is focusing on 3D visualization and software optimization and real-time tracking to advance biomedical imaging performances. And for today, Patrick will actually focus on MPI as a game changer in medical imaging. So without further ado, Patrick, floor is yours.
Yeah, Leila, thank you. Thank you all for coming in. And so I am, and it's a pleasure for me here to see all the people from this nexMPI group. And in the next, let's say 2 to 3 hours, I'll give you a short overview about MPI and what I was doing the last now 15 years now, I think. And so my first slide is when you're asking or when you're working today with a new topic, then of course you're working with ChatGPT and all the different AI agents and so on. And this is one of the image you get out when you ask ChatGPT about can you provide me an image for MPI and its hardware components? You can see a lot of different things. So let's starting. Let's see the laser pointer. We're starting with scanner, of course, and then different parts from the receive coil, the image reconstruction part, signal generators, and so on and so on. So many parts you have to put together just to let an MPI system grows. And I want to get you a little bit on a journey. What me and my group experienced in the last 15 years about when I started here at the university with the question, okay, let's build up an MPI system. And I said, yes, sure, why not? Let's start this nice new way. And we found out there's so many different things which can occur, but at the end of the day, it is a long journey, but it's a lot of fun. All right, so again, let's ask ChatGPT about what is magnetic particle imaging. You get a lot of information, and so we tried this for the first time 5 years ago. And 5 years ago, a lot of bullshit came out by ChatGPT and AI agents. But now at this time, everything is fine. So a lot of information, everything is almost correct. But shrink it down. MPI is a non-invasive medical imaging technique that creates 3D images of the distribution of superparamagnetic nanoparticles, usually iron oxide, inside the body. And also again, ChatGPT provide me an image for that. You can get this image and you see, cool, MPI also has now some human-sized MPI scanners. And something is here wrong, obviously, with should be the heart, but seems more than the liver. Okay, so there maybe are some funny things what still happen. And also this huge machine, unfortunately, until now, we do not have such machines, but I think the community is on a good way. And but let's see, what is MPI? And MPI, magnetic particle imaging, so it's we are using particles, and we are often compared to MRI, magnetic resonance imaging. And also in MRI, you are using contrast agents for, as the name said, to enhance the contrast between different tissues. And since about, I would say, 8 years now, they stopped using iron oxide tracers, contrast agents, and now using gadolinium-based ones. And we are still, and this one was one of the starting points in MPI at this time when for MI also the iron oxide based contrast agents are used or have been used for different applications. And then the question occurs: what happens when some iron oxide nanoparticles are inside an MRI scan? And just to get an idea what should happen when you put in some iron oxide nanoparticle on an MRI scanner, then the magnetic fields is distorted, and at the end of the day, the image is blurred, or the signal goes down, and everything is lost. And so just to get an idea, here on the right side, you get a low field MRI system of 3 Franconian grapes. And something seems to be different here in the middle one. So there is a signal loss. And now the question is, from the MR side, is there an air bubble or is there something else? And so this was one of the ideas of MPI. Okay, now with MPI, we can also look at this, and as a tracer-based technology, which is only sensitive on this iron oxide nanoparticles, we are able to distinguish between air bubbles, or of course here for this test we can show that in the middle grape there is the middle grape has been filled with some of the resovis. Resovis is then or was one of the contrast agents for MRI, and this particle system works quite well also for MPI, and that was one of the starting points. Okay, so we have now the possibility to use a new technology, which is comparable as a tracer-based technology to PET or SPECT. We just see the tracer, and you have to introduce the tracer into the body, and you get a positive contrast and with a highly sensitive signal, and so on. But still, MRI is not MPI. In MRI, you have to use quite homogeneous magnetic fields for generating the signals. And in MPI, it's completely different. The only one is we're also using magnetic fields, but we still we need strong gradients. And how we can use these gradients in MPI to create images, let's see in a few slides. So, but let's start with the particle system itself. Everything starts 2005 with this paper. It is from the Philips group, and they came up with a tomographic imaging using the nonlinear response of magnetic particles. And here on the right side, you can see the first scanner. And I think, Volkmar, this scanner is still working, and it's available in Aachen. And it's really nice to see that this is still running. And here in the middle, one of the first MPI images. And how does it work? So what is a superparamagnetic iron oxide nanoparticle? Superparamagnetic iron oxide nanoparticles are, let's say, quite small particles, which have, you can see on the left side, which has only one domain or one homogeneous magnetization. Or in other words, make it simple, you can see these tiny particles as small magnets. So superparamagnetic just means you have one wise domain, and so each of the particles can be seen as tiny magnets. And when you now put together a lot of these magnets, or these quite small particles in an ensemble, then the magnetization of this ensemble just is zero, just seen from the outside, because of the stochastical distribution of the particles. So with only without an external magnetic field, no magnetization can be seen. And now when bringing this particle system near to an external magnetic field, here for example in a permanent magnet, then all the particles align to the external magnetic field, and the magnetization of this ensemble starts to grow. And it grows until a certain point, obviously. So when all the particles are aligned to the external magnetic fields, then the maximum of magnetization was reached. And so we call then and this is called the saturation magnetization. As a physicist, of course, we are trying to describe this behavior, and we can do this with this nice nonlinear magnetization curve. It's called the Langevin function, and physicists like nonlinear magnetization curves because you can see it here with an external magnetic field. So with a small change in the external magnetic field, you can produce or create a quite high change in the magnetization. And with this is the basic effect or the basic idea behind MPI, just using this nonlinear magnetization response. How we can do that? When you now apply external magnetic fields, sinusoidal magnetic field with a given frequency, and when this field is strong enough or provides an amplitude which is strong enough that this ensemble, the magnetization of the ensemble, can reach the magnetization, the saturation magnetization, as you can see here, then we can track the magnetization over time. So, and this creates this nice, let's say, rectangular shaped magnetization curve. And in MPI, normally you're using additional electromagnets or coil systems for inductively measure the signal. So, which means we measure the duration of the magnetization over the time. You can calculate this here as well. And at the end, from this rectangular shaped signal, this blue curve with these typical peaks of the changes of the magnetization occur, and then when you afterwards starts Fourier transformation, you can see this nice forest of different harmonics. And these are specific harmonics. These are higher harmonics of the excitation frequency. So this frequency you put in is a single frequency with a defined frequency, and you get out higher, in this case, odd higher harmonics, which are created by the particle system itself. And these higher harmonics, this is the signal we want to acquire, we want to see, because all the information is from the particle system itself, and also later on for the encoding is stored here in these higher harmonics of this system. So, for example, we have here 3 different particle systems. So, one is the Perimac, it's a specific particle system from a company here in Germany. Ferahem is also a medical particle system, and also magnetosomes. Magnetosomes are quite specific particle system which came from magnetotactic bacteria, which are creating small particles in their body just to align the magnetic field of the Earth. And all the particles you can see creates different responses. So which means for different particle systems, you get different information. And for example, here in the middle, you get the spectrum of the particles, and you can see the higher harmonics, and you can see different slopes of these higher harmonics. Or on the left side, this hysteresis. So huge hysteresis areas, for example, can be used for better heating. So you can use these particle systems or these particles also for locally heating. And so you have different applications you can do with that. But yeah, this is the point I want to address. All the particles will provide different different features. And so Perimac, for example, is quite good for imaging processes. Magnetosomes, in theory, they're also quite good, but they're also, for example, usable for hyperthermia as well. By the way, this Magnetus beryllium is the micro of the year 2019. So I find that out, and it's quite funny. You can see here this the bacteria, and inside the small black dots, these are the particles. And there's a group here in Bayreuth next to Würzburg, which are using these bacteria for their particle production. So, but what is the reason for that? So why are the particles, or show the particles so different behaviors? And there are two major relaxation effects. One is the Néel relaxation and one is the Brown relaxation. What is the difference? The Brown relaxation on the right side means that the entire particle is rotated when the external magnetic field changes. The Néel relaxation means that not the particle itself rotates, but the magnetization inside the particle will follow the external magnetic field. And you can find this behavior that's for smaller particles, so let's say in the range below 10 nanometers core size, that the Néel relaxation is the dominating effect. And for particles, let's say below 25 or 30 nanometers, the Brown relaxation dominates the effect. And there's a quite interesting area between, and this is also quite interesting from the academic side, the difference between, let's say, 10 to 25 nanometers. And we know from the last 15 years, there's an optimal size for MPI imaging as between 20 to 30 nanometer particles. And when you have a look at this, the formulas for the different relaxation effects, you can see that a lot of parameters has influence to this parameters to this timings. And for example, the size or the anisotropy or the shape of the particle. Of course, then when you have the Brownian relaxation effect is dominating, then also the viscosity of the environmental medium will influence the signal generation, which can be quite annoying, but I can show you something, some application where you can use this as well. But also the temperature will affect your particle signal. And there's so many more: size distribution, core structure, chemical interaction, and also the particle-particle interaction as well. So, which means, I'm also here in the working a lot with MRI machines, and so from this point of view, MRI seems to be quite simple from this point of view, and the MPI part is more difficult because of the particle system itself. Because you have so many different parameters which have influence on the signal generation and then afterwards as well on the imaging results. So we can try to simulate this. We are starting here also in Würzburg different projects to do that. In the first step, just by simulating the Brownian rotation. And you can see it's actually quite simple. So we have two terms, the deterministic part and also the stochastic part. And then you can find out, okay, so you can simulate or you can emulate the same or similar effects. And so it's a good way to get a deeper understanding of the signal generation in MPI. And this is quite important at the moment, I think, that we get an idea what you can do with this let's say, features of the particle systems itself. That brings me to one of the applications we developed here in Würzburg. It's called Compass, and it was during the pandemic situation. And it's a short reminder. I know, I think everybody knows that. So there are different types of rapid tests outside. And our aim was to provide a real rapid test. And the idea was, when we're using a magnetic nanoparticle and put an antibody or linker molecule on the surface, then we are able to see the antigen or antibody from a serum of a patient. And by doing this, then the compartments will stick together. The idea was that the particle system itself grows up a little bit. So, and what happens then? I have here a short simulation. Let's have a look. So you can see that the small particle can follow quite more rapid or quite fastly the external magnetic field, and the particle with the bound antigen, or here the antibody on the surface, are slightly bigger. And so they take more time to follow the external magnetic field. And so there's a difference. And that was the idea. So it's quite the same as we know from these ice dances. And that was the basic idea behind the compass effect, that we can now distinguish between the bound and the unbound state of this particle system. And when you have the linker molecule highly specific for SARS-CoV-2 antibody, for example, then you can provide a real rapid test. And real rapid test means here that we are able to this time to get an information within a few seconds by adding the SARS antibody to the sample, and we can also distinguish between high, medium, and low. So also the quantitative results are doable with this really nice tests. That was the test at this time. Unfortunately, we take too long to bring this on the market, so we are waiting for the next pandemic situation to use this. So if you find one, then give me a call. We have these machines here. So that brings me to this first summary. What we learned. So MPI is based, or MPS, the spectroscopy part is based on a nonlinear response of the magnetization of superparamagnetic iron oxide nanoparticles. So these particles can be completely different, but the signal is complex, but we are able to also simulate these particles and also the signal behavior in a certain for different parameters, just to get an idea what is the influence on the different areas. And it's not a bug, or it's not a problem, I would say. It's more a feature of the particles, and we are one of the groups just looking what you can do with this different behaviors of the particles, and one of them you can see it's a compass effect. So can be also useful. So that brings me to from the spectroscopic part to the scanner part. So how we can use this for imaging. And for example, we have here a small rodent, and we have 3 different areas with a point-like sample of a particle system. And now the question is how can we encode these 3 areas within the mouse? And in Würzburg, we started 2010 by building up the first MPI scanner, and we called our scanner type the traveling wave MPI scanner. And in a few slides, you know why. And firstly, we started with 16 single coils. So it's just an electric coil, and by driving all the coils with a sinusoidal current, all the same currents, all the same amplitudes, and so on, you can see that the particle systems, so the different areas, change their magnetization. So they follow the Langevin function, and when they reach the saturation area, then the saturation magnetization is reached. And within sinusoidal magnetic field also, the magnetization will follow. And by adding and receive coil, we can now measuring inductively the signal. You remember it's the duration of the magnetization over the time. And you can see for every time the magnetization or the external magnetic field is near 0, then the magnetization flips from the positive to the negative side. And by this flipping, you can see the peak. One of the peaks is created in the receive chain. And we can now see, okay, there is something in this, let's say scanner, but we cannot distinguish where it is. So we built up here a classical spectrometer. So the easiest way. Everybody can do that also at home. But we want to see where exactly it is in the scanner. And our idea was to to change the current distribution over this linear gradient array. And we do that here, for example, in a way that we have a current distribution which shows this sinusoidal magnetic field behavior. And then you can see these three particles, for example, or ensembles, have different states. And now by doing this dynamically, so just running all these coils with the same frequency, with the same amplitude, but with a different phase between the adjacent coils, you can create this running wave or the traveling wave through the scanner. And now you can see over the time, the states of the particles or particle ensemble will change. And these 0 points, so the areas where the magnetization is almost zero, the external magnetic field is also almost zero. We have a name for this in the community, is the field-free region. Here in this case is a specific form of the field-free point. We will also see later on that there are field-free line scanners. So Maxwell equations can produce different behaviors. And again, by adding an receive coil, you can see every time one of the field-free points runs through an ensemble, then the magnetization flips from the one side to the other side. And each flipping will produce a peak in the receive coil. And voila, we have now in 1D encoding in our scanner. But we want more. We want to go to 3D. So here's the same in 3D. So we open up this system, and the main system generates the magnetic fields into the Z direction. And we will add a subtle coil system for the Y or for the X direction, another subtle coil system for the Y direction, and of course the receive coil. And by adding these subtle coils, we are able to move and to displace the field-free points in different directions. And so the idea is then to cover the entire field of view step by step or point by point. That was the scanner, our first version of the MPI scanner. So here in this nice aluminum board box, here on the side you can see the gradient system, and of course you see that that are not only 16. Here we have 20 coils. We need this because we have a problem with the coil-coil interaction, and we started also with 3D printing all the parts. So we can here see the subtle coils. Here's the first subtle coil on one side, and here nested in is the second one, and the receive coil is built also in the middle of this system. Just to see how strong such a system is, you can see here's the movie of one of the first runnings. So we run that with 60 amps per channel, 5 kilowatts of power. We put in here a wrench, small one, and we have a traveling field. So when we now create one of the shots, you can just build up a railgun, similar a railgun-like system. And we tested this out for other stuff, and the record in our labs is at the moment shooting up different projectiles with up to I would say it's 35 meter per second. So we can also do that. Use this for other stuff. To run an MPI system, you need much more. Here's a short overview. So of course you need the control units from the signal generator in the data processing area. You also need the excitation chain. So this here is the scanner itself, so the call system. You need additional coupling systems. You need amplifiers. We are using audio amplifiers. You need low pass filters and different stuff just to clean up the signal before you can generate the magnetic fields. And then on the other side, with the receive coil, you have different steps to clean up also the signal. And then before you can digitize the signal and then produce the images out of that. It was the scanner in an also quite early version. Here's on the left side is the scanner. Here you can see the different audio amplifiers. Here's the signal generation area, audio amplifiers, and here is the area for the digitization of the data and also the data processing itself. So on the left, you can see now this for a quite easy example. So this black areas represents the field-free points, and the field-free points are here steered on a sinusoidal trajectory on a slice through the scanner. And of course, when you do that, you can reach each point of the field of view after a while. And for 3D imaging, you can also do this by rotating this pattern, for example, as here visualized on the left. And then you can create different ways of images. For example, here, this nice spiral one, or one of the first 2D images we can produce. And also, you can also put in different other stuff here. For example, there's in stone. I found somewhere, when you look into this area, you can find that there's something which also produce quite nice signal. And it turns out that this is a magnetite included into the stone. So we could also perform then micro CT for that, just to get an idea what happens there. So traveling wave MPI uses, as the name said, a traveling wave for the encoding process. And everything is handcrafted. So because until common time, nobody was able to provide such things, unfortunately. And so far, we are just using audio amplifiers, which makes this technology almost quite inexpensive. But of course, there are also other advantages using low frequencies, especially when you go to larger systems, which are more specific for the medical applications. So maybe some slides to the process of the imaging. I will run a little bit faster through that, but just to get an idea how many steps are required to come from the standard signal to an image. And here again, this traveling wave concept, the field-free point running through a point-like sample, and over the time you get this point-like these peaks of the signal, and by Fourier transformation you get the odd higher harmonics of the excitation frequency. So everything's fine. Okay. When you're now using, for example, for a 2D scan, you're using a second frequency. So you have the first one, so it's the traveling frequency from left to the right, and you have then for imaging or for encoding a slice, you need a second frequency, and the second frequency here is from up to down. And with the second frequency, now you get, from the second frequency, you also get higher harmonics of the particle system as the magnetization response. And together, you get a whole bunch of higher harmonics in the spectrum of a signal which is created within such a scanning mode. And of course, when you now at the third frequency, which you might need for 3D imaging, then you get as well higher harmonics of the third frequency, and all these higher frequencies, frequencies will combine together and will fill up your spectrum quite rapidly. So at the end, you end up with more than a couple of hundreds higher harmonics, and you have to collect as much as possible to reconstruct a nice image. There are a lot of problems when you try to work with a high bandwidth, because you have a lot of distortions coming up from a receive chain from the different components. So here, as an example, you have an amplitude mismatch or amplitude weighting of this coil here, and also the phase changes over the frequency quite dramatically, and you have to get rid of that and have to correct that. And so I will jump a little bit more over that. So you get influence of all the components on the frequency and on the signal, and you have look for correct that, and you can do that by just determining the transfer function, and then you can calculate out the distortions. And it's quite easy to do that. You just have to use a small coil. You put this coil into your scanner, and you then by sending a specific frequency, for example, over the small coil, then you can measure on the receive side what will change in amplitude, what is the change of the amplitude and the phase at this specific frequency. And when you do this for all the different frequencies in your spectrum, then you can acquire the transfer function, and with this transfer function you can then correct your system. This is one of the most important steps in an MPI scanner system. And for example, the Bruker MPI system has an own robot built in, and you have to do that every time before you can measure with these systems. But there are such more different steps to do. So for example, baseline correction, you have to do a filtering in K-space, you have to generate the raw images when you're using MPIs, TWMPI systems, then of course the imaging progress itself, geometry correction, combination of 2D projections for 3D imaging, and also the 3D image reconstruction process. So I will jump over this a little bit more fastly. So here, for example, the raw image generation. When you have questions on that, please give me that later. And also here, for example, this is also quite interesting for the different particles. You can remember the different particle systems will provide or produce different spectrum and also different hysteresis and also different images, of course. So here, for example, the MITO 511 is a quite good particle system, and this point split function looks really nice here, and also the reconstruction looks quite fine. But different particle system will provide completely distorted point split functions and such, and then of course within a standardized reconstruction, the reconstruction process will fail. So all the 3D is possible. We are using here some ideas from the CT world. So you are creating sinograms and using radon transformation and so on. But at the end of the day, you can end up with an image. There's another way for image reconstruction, and it's the system matrix approach. And we are calling this often the black box approach, because what you do, you put in, the idea is quite simple. You have a robot, or you have a robot, and you put in a small sample of a new particle system. You have no idea about this. And then for each of the positions in your scanner, you will acquire a signal. So, and you put the signal for all the positions, you put the signal into a system, a so-called system matrix. And the only thing you have to do then is to calculate an inverse of this system matrix, and then you can solve your signal problem. And that's it. So this is the basic idea. So yeah, just performing the system matrix, the system matrix measurements, and then you can use different mathematically sophisticated algorithms to solve this. So here, for example, the Tikhonov algorithm for the regularization, for the iterative regularization, and then you can end up with the image as well. Problem, or one of the issues of this approach, is the long time you need for acquiring the system matrix in a prior step. So when you're using 3D, when you want to do 3D imaging, you will end up with a couple of thousands of voxels, and you need much more, quite a long time to get this information. Okay, so MPI consists of higher harmonics. Of course, when you're using imaging, you will end up with quite a lot of these higher harmonics. Real MPI systems are interesting to handle because you need a lot of different steps to get rid of all the distortions part and so on. Also, the data processing is quite important to have in mind. And also there are different ways for the reconstruction. So the X space and also the K space. So the X space is the image-based reconstruction part, and the K space the mentioned system matrix approach, for example. So we have a software developed here in Würzburg. It's now called OctoView, and you can see quite a small overview. So we put together all these different processes and steps into one software just to use them with different scanners and also to use them with different simulation models. So, okay, now we built up the first scanner, quite cool. And then, of course, we want to go to the first medical steps, medical applications. And one of them is, so in Würzburg, we developed the real-time systems. And for that, we have to optimize different steps. And here, for example, we tried the sensitivity of an online reconstruction. So that means no averaging. And you end up with it's a quite old one, 2018, yes. But it's a quite good sensitivity. Also, of course, the online reconstruction, you can see on the right side at 40 centimeter per second, we shoot a bolus through the scanner, and all the reconstruction processes are working quite well. Also, the spatial resolution is important. Here, for example, it's also in quite small small animal scanner, and we are using here a quite high gradient, but we can reach a spatial resolution in the range of 330 micrometers, so it's possible. We also learned that these days that this is quite annoying to handle this amount of data you can produce within just one image. So a lot of things you have to be solved in the future, of course, but it's doable. So the spatial resolution, the theoretical one, there's a formula which looks like this, and you can see it's directly proportional to the temperature. And of course, when you're going to in vivo, then you cannot, or it's quite difficult to go down with the temperature. Of course, then here we have the parameters for the particle system itself, which means larger particles means a better signal, or a better spatial resolution, and also a higher magnetization, saturation magnetization leads to a better spatial resolution. I said the best particle size is between 20 to 25 nanometers. Why we are not using 100 nanometer particles? Well, because you can remember of the Brownian relaxation. So the problem is when you're using large particles, then the particles cannot follow anymore in real time the external magnetic field, and thus the image just starts to blur, and you will also lost again the spatial resolution. And here's the gradient itself. So higher gradients means better spatial resolution as well. And also the particle system, of course, had different influences. Here, for example, the ResoBist, so the same scanner setup, ResoBist with this sample here, and LoadSpin was a particle system from a Washington company. Doesn't exist anymore, unfortunately. It's LoadSpin. And you can see that there are optimized particles out, which can provide a better performance for imaging. Also, the real-time reconstruction capability, here we tested it for the first time. Here we put in a small point-like sample in the 3D scanner, and you can see, you can hear it. The small beeps is one of the imaging process. So with each of the beeps, one sequence is created to get the image of or to get the information of the entire volume, and the reconstruction process only needs here about 50 milliseconds. So with that, we performed the first in vivo imaging. So with the background information from an MR system, and we put into the tail vein resolvist, and you can see here the resolvist starts to go up the vena cava into the beating mouse heart. And just looking in this specific region, here you can see in real time the heart rate, and after this Fourier spectrum, it's 150 milliseconds heartbeat. So that's everything is fine with this animal, or was fine. There are a lot of different more possibilities, molecular imaging. So we also intravenously use this with labeled cells. So here's a small cancer lung model. So the prepared cells then starts to go into the lung. We can also make this visible, and also a more sophisticated approach was this one, is then graft versus host disease, where we can actively label the specific cells in vivo with specific particles. We also tried more than 10 years ago of functional MPI with the carbon oxygen switching, and you can see it also works quite well. Then we tested for the first time MPI in combination with CT. And we can then show that it's also possible to use both imaging modalities simultaneously, which is also quite interesting. So we built up a specific scanner for that with a CT window. You will see the CT window later on. That was the first trial just to check out if this is possible. So different applications you can do with this MPI thing. As I mentioned, we in Würzburg are mainly working on the real-time thing. So in angioplasty, stenting, and instrument tracking, and so on. So over the last 15 years, different scanner types pops up. So the left one, for example, is the first from the Philips group. They are provided this idea with a field-free point system, three different excitation fields on a lizard-juice trajectory. Then we have a field-free line scanner. So as I mentioned, field-free line has a quite interesting advantage because it's much more sensitive. But the problem was that the hardware, the complexity of the hardware was so annoying that these systems are quite hard to handle. And then with our TWMPI, we have a completely different approach. And our idea was then to combine the traveling wave approach with a field-free line scanner. And I will go a little bit faster also over that. So we come up here from a field-free point to a field-free line. We then change the coils. So these yellow ones are different electric coils, creating different field directions with this red arrows. We are using multiple of these cross coil systems. Then the traveling wave approach again. So we can generate the traveling field-free lines through the scanner. And by adding additional coils, we then also can displace these field-free lines. And of course, by adding this in another direction again, we can generate quite easily a fully electrical driven field-free line scanner. So it turns out that this system looks quite complex, but at the end of the day, it's quite easy to handle or easy to build, and it's more handleable than it looks at the first glance. And one of the advantages is also that you can create different trajectories with this scanner. And we are just working on figuring out what is the different and what is a good or a bad trajectory at the moment. But it's still work in progress. You can see the system is quite small. So this is a small animal scanner, the first one of this type. So, and this is a normal sized banana. And since now 1 year or a little bit more than 1 year, we also have the possibility to provide this as a ready-to-use product. With this, we can do a lot of funny stuff. For example, here, real-time flow visualization in an aneurysm phantom. So we can reach here 20 volumes per second, which is really, really interesting. So this is one of the topics we are working on here in Würzburg. But one thing, of course, is just make it bigger. And there are different approaches. Here from Philips, human-sized. Here from also from Philips and also Hamburg, head size scanner. Here you can see a scanner system from Larry Wald in Boston. It's 1.5 tons of rotating gantry, which is a really, really heavy machine. Also a head size scanner, that's quite nice. Here from Mitsubishi, also head size scanner. There is a scanner from, where is it? Korea, I think, which uses a superconducting magnet. It's really, really interesting. And there's another spin-off from the Berkeley group, Magnetic Insights. They're building also a head scanner. It looks like this. And from the Oakland University, from Alexei, they are building a single-sided system, which can provide you a much better handling of the field of view, of course. And our idea was also to go this way. And how we can do that. The first idea was just to build a huge TWMPI scanner, but the calculations turned out that it is not possible. 2 megawatt power dissipation is a little bit too much. And so we shrink down the system to fit in just a leg. And it's more handleable and more doable. And here's the system it looks like. One of the goals was it makes it usable within an angiography lab, so with a CT scanner or in an X-ray scanner, and it's also in field-free line scanner. You can see it on the left. During the pandemic situation, we have a lot of time to build up the system. So we perform simulations, CAD, 3D printing, coiler sampling, and you end up with this quite nicely lightweighted and portable system. And of course, you need, again, a lot of parts along the system. So from the transmit-receive chains, the console, the periphery, amplifier cabinets, then the real-time visualization part, of course, the receive coil and the phantoms, and a pump to simulate some realistic blood flow in the system. So here's one of a quite early movie about this. I think it was the second time this system was running. So everything is safe in this lab, of course. So this is the scanner. I have here in my hand now a small sample, and I put it with my hand into the scanner, and then the system starts to run. You can hear it again performing the images, and on the right side you see the reconstruction, or you also hear the real-time reconstruction on the image. So it was the first time that the scanner performs some interesting images. Okay, so we can do more with that, of course. Vessel structures, aneurysms, stenosis we can use. We also can track instruments, guide wires, and balloon catheters. And then we could show that it is possible to perform real-time MPI-guided PTA, so percutaneous transluminal angiography within a huge scanner. So angiography, the balloon positioning, the dilatation, so to open up the stenosis, and then, of course, the angiography after the treatment. And because it's a portable system, we are using this first time in a real or more realistic environment. So we put everything together onto some wheels, and then we brought it into the catheter lab. And here you can see it live running with an X-ray simultaneously, producing on the left side the images from the X-ray, on the right side the images from the MPI scanner. And here you can see the scanner, and Stefan is providing a bolus of particles running through a sample in the scanner, and pose the scanner X-ray and NPI get the information. So we also did this in a human body donor. So we get the possibility to do that in an the latest or the most realistic before the in vivo imaging. And also again, we put everything together. Here's the body donor. And again, we put in a bolus. You can see the X-ray and also the NPI at the same time. And that was the first time we can show that as well. So with different findings. And so I'm a little bit over the time. I'm so sorry for that. But hopefully you get a little bit an info about the MPI thing. And I want to thank my group, all the founders. We also have another project. It's called the Stroke Cap, Mobile Stroke Diagnostics. And you can see in Würzburg, we're doing a lot with this particle systems and with magnetic fields. And it's a quite interesting part. And so I'm so happy that this nexMPI project starts. And we will see how many of you we can get into this community, and hopefully we will grow in the next few years much more. And so when you have some questions, so please let me know. And
fantastic, as always, very inspiring, Patrick. Thank you very much. Anyone would like to ask some questions, please raise a hand. Alternatively, you could always write your question in the chat option. We will follow that as well. So let's see. Anyone a question? Not at this moment. I do have a zillion question, as you already probably know, Patrick. So I'll start with few. One, and then to start with, and then I'll see if there are any other questions from the current participants in this webinar. You show wonderful results so far with reasonably high TRL levels for your devices. And I'm not trying to tease you, but I will be really wondering, for Germany, what is your, let's say, top three problems in translating that into a real clinical trials to start with? How far are you?
It's in Germany and also in the EU is quite difficult at the moment with this scanner. So we have a lot of talks in the last few months with different commissions, and also with the ethic commission at the University Hospital. Especially with the Stroke Cap project. And but at the end of the day, at the moment, we have just the problem of the safety issues with the systems itself. So it's a hardware problem at the moment. So what we need is a little bit time and money to get the permission from TÜV or whatever to bring the systems into a clinical environment and to use them with the first humans.
So are we talking about EMC related issues, compatibility, and basically electromagnetic safety, right?
Exactly. So this is one of the major things, of course, from the method, from the signal generation itself, also from the safety stuff,
patient and the personnel, I suppose, as well. Yeah,
but it's handleable. I think it's handleable, and
it is. From my experience, it is definitely is.
We are looking here
yeah.
for the best ways. We also get the permission now from the Ethic Commission here to get into the first in vivo imaging processes, and we will see how far we can put this. And so everything is doable. So all my hands are working. And my hands are quite often in this scanner. So
yeah, but it is a painful procedure to get from zero to clinical trial to first clinical trial.
Oh yes, it is, and you need a little bit of money. So if somebody is hearing here, so we have
a lot of patience, I suppose. A lot of patience to write all those documents as well. Anyways, any other questions so far from the audience?
I think it was too many information.
let me see if someone on chat
It's through the
about
chat,
the
maybe.
recording and sharing slides. About slides, I don't know. Patrick, would you be willing to share the slides? The recording itself, will be shared through the website, nexMPI website, as soon as we just go through the recording and store it and on a specific site.
Sure. So the slides. So when somebody needs some of the slides, of course, just write me an email. We can handle this, of course. But it's about
Okay.
1 GB, a huge PowerPoint, so it's quite difficult to send this via email.
Course. Another question, let me see, excellent presentation question about handheld MPI. What do you think are the potential clinical application scenarios for the, let's say, handheld MPI devices?
Yeah, handheld devices. So I know there are. So we also tried a lot with these handheld thingies. So the MPS mouse we developed here. So it's a mobile universal surface explorer. It's quite similar to this NMR mouse from the Aachen group, from Bernhard Blümich. I would say these small devices, and there are some in there's a device which can be used for lymph node detection, I think, and they also have the permission to do that in patients. I think
Who are they, Patrick?
I'm not sure where they are. I think it's the Netherlands, maybe.
Oh, you're referring to my research, I suppose, to the handheld devices,
Yeah.
but those are signal measurements, so not a handheld MPI devices,
Okay,
right?
handheld
So
MPI.
there is a difference.
Okay.
Yes, we use that
Yeah.
in clinical trials for lymph node detection indeed, but I suppose the question, I'm not sure,
Handheld
the
MPIs.
one that asked that question, please switch on, and if you need to go into discussion, please do, if that is an option. But I think the question is really regarding MPI handheld devices.
Okay, so I have no idea if there are some, because it's quite difficult to handle all the required encoding fields and gradients you need for the encoding to put this into a smaller, handheld device. There are a lot of approaches. So we also tried a lot such to use this spectrometers, this handheld spectrometers, but then positioning tracking just to get an idea. Okay, so how you can translate this positioning tracking through a surface image and so on. But I think there you can do a lot of stuff, I would say. But then, of course, the question for a good application for these so is I have no idea where if there are some. But for example, this lymph node detection, I would say this is a quite good approach, definitely. And from the imaging part, I would say this of course this way we are going at the moment with this smaller portable systems which are usable with other modalities is a good way for the for interventional purposes. And so I saw a lot of huge scanners and also showed you some of the slides. My problem often is that the basic idea about MPI because is lost with this other scanners. So MPI is a really fast technique, and this is one of the things we are trying to move the borders, of course, just to show, okay, so we can produce within 10 to 20 milliseconds a whole body scan. But there are also scanners outside where a whole body scan needs about 40 minutes. And it doesn't make sense in my world. Yeah, so MPI is inexpensive and fast. And I think this is one of the strengths of MPI. And so from this perspective, I would say you have to we are still looking for the killer application, of course, and we get this nice discussions also on the IWMPI this year. And of course, it's a little bit struggling, but I think we have now everything. So we have the scanners, we have also the human-sized systems. We also have here in Europe the possibility to use Resotran as in an off-label use, also for MPI. And I would say, just do it. Just do it now.
Brilliant. Thank you. Thank you for answer. Are there any other questions? Burning questions so far? I really have a lot of questions, but I
in the
will not
chat,
ask them.
we have another
Gabriel, yes.
Leila, I think in the chat we have another question.
We have a question from a student asking about recommendation for relevant literatures. I think that would be fair to ask a student to email whoever is interesting from discussion, either Patrick, me, or someone else from nexMPI, to provide a guided answer, because this is a kind of general question with a difficult answer at this point. Anyone else?
Yeah. So maybe some words to the literature. It is quite a lot what you now can find at the moment when you ask Google for MPI, and it's horrible. And I have a lot of discussions with also with other students to get an idea. Okay, what is important, what's not. But I think in the last couple of months there came out a lot of different reviews, which gives you which can provide a quite nice overview about this topic. So just look for magnetic particle imaging and reviews maybe. But of course, you can also write an email. It's not a problem.
Brilliant. Waiting for a few more seconds for other questions to arise. No. I'll keep my questions, I suppose, because we are over time in that sense. I'd like to thank you, Patrick, for your wonderful presentation, as always, and inspiring work. Amazing amount of work from, I wouldn't say such a small group, but yet the output per capita is huge on your side. So thank you very much.
Thank you.
Take care, and we will share this information, the recording, through the nexMPI website. Take care. Bye-bye.
All right.